So welcome to this video. This is the first video in a playlist on real analysis. Now, we are trying to go towards a definition of the real numbers, which is a starting point for all of real analysis. In order to do that, as part of the definition of the real numbers, we are going to need to understand what is meant by an ordered field, and that is the reason for this video. Now, I warn you, I personally do not find this a particularly thrilling topic. However, it is an extremely important part of the definition of the real numbers, so it is necessary to cover this. So first, a warning. This video is really going to be on orderings and what is meant by an ordered field. It is not intended to explain what is meant by a field. I'm going to assume that as prerequisite knowledge. So when I say something like a field is a commutative ring where all elements bar the additive identity has a multiplicative inverse, I'm hoping that you understand that statement. I'm also hoping that you've potentially seen the construction of the field of rational numbers from the integral domain of the integers. If you're not familiar with that content, then may I suggest that you leave this video and instead go and learn some algebra, because understanding algebra is more foundational than understanding real analysis. And really, I think it's not a good idea to try and rigorously understand the foundations of the real numbers when you don't even rigorously understand the foundations of the rational numbers. So now that we've said that, let's begin discussing ordering and what is meant by putting order properties on a set. So let's illustrate this with an example. So we have here a set that we've called the set S, and this bubble here represents our set. And then inside the set we have three symbols, and these symbols, I just pulled them out of thin air. So they are, of course, some of maths' favourite symbols. So we have the symbol x, we have the symbol phi, and we have the symbol theta. So this set consists of three elements, x, phi, and theta. Now, if you want to put an order on this set, to make it an ordered set, that is exactly what you would intuitively imagine it to be. It means that we are going to specify which elements are less than other elements. We're going to put the elements in a line where the more leftward you are on the line, it means you're lower down. The more rightward you are on the line, it means you're higher up. So here are some examples of orderings that I can put of these three elements. So here we have x is the smallest one, then we have phi in the middle, and then we have theta at the top. Here's another example of an ordering where x again has been put at the bottom, and then phi this time is at the top, and then theta is in the middle. So now the question is, how can you capture or encode the information of this ordering for the set without the picture? Well, what you can do is you can create a table, which is what I've done here for this top ordering. So you can create a table where you're going to have all of the elements of the set in the column here and also in the row here, and then we're going to have inside this table answers that are either ticks or crosses for true or false. If you were a keen computer scientist, you could ask to use ones and zeros instead. So you could use 1 for a tick and 0 for a cross. And what this table is going to say for each two elements is whether it's true that the element here in the column is less than or equal to the element in the row here. So if we look at an entry, x with x, what we are asking, is it true that x is less than or equal to x? Well, of course that's true because they're equal to one another. Then this next entry here, is it true that x is less than or equal to phi? Well, we're encoding this ordering here. Yes, that is true. X is less than phi. Then the next one, is it true that x is less than theta? Yes, it's true. So there's a tick there. Of course, there's going to be ticks in all of these entries here because you're asking, is the element equal to itself? So you're going to have ticks all along that diagonal there. And then these opposite entries down here are now going to be crosses because they're asking the opposite question. So here we're asking, is phi less than or equal to x? Well, of course, that's not true because actually phi is greater than x. And then likewise for these two entries here. And this table is abstractly encoding all of the information of this picture here. So actually you could now get rid of the picture and you could just have your set with this abstract table of information here, which you could actually view as being a function from the Cartesian product of the set with itself onto a set containing tick and cross, or 1 and 0. So the set with that structure with all that information in, is actually encoding the same thing as the picture. It's describing the same thing as the picture. So this with this is an ordered set. Just to explain what I meant about the Cartesian product in a little bit more detail. So the Cartesian product of the set with itself is all Cartesian pairs of elements from the set. So it's all things of the form x, y, where x and y are both elements of the set. So every single one of the 9 combinations in this table is a Cartesian pair within this set. So x with x is in there, x with phi is in there, phi with x is in there. All of the 9 entries here are going to have a Cartesian pair, a related Cartesian pair over here. So actually you could view the information of this table being a function from that set of Cartesian products, or from the set of all the entries here, to the set that contains just tick and cross, which are the answers in the table here. So that's what I was meaning when I said you can view this table, if you like, as a function from the Cartesian product to the set of tick and cross, or the set of 1 and 0 if you wanted to use 1 for tick and 0 for cross. So now an interesting question to ask is, what properties does a table like this have to obey in order for it to actually describe a proper order, a picture like this? If I just make up a table with random ticks and crosses all over the place, would that actually be sensible? Would it mean anything? Would it relate to a picture like this? Well, here we go. Here is one that I've made, a random table where I've made up the answers, and you can see quite clearly that this is absolute rubbish, because I've got, that x is not less than or equal to x, and phi is not less than or equal to phi, and I've got that phi is less than or equal to x, but also x is less than or equal to phi. This is obviously rubbish. So this structure, this property that we've put on the set, this order property, has to obey certain rules in order to actually be sensible, to mean anything. So there are 3 axioms then that order properties must obey, and we'll go through these now. So I've written the first one down here. So axiom number 1 is, for all x is an element of the set, so now x is not just the symbol we're using here, x is the general member of the set, it must be true that that element is less than or equal to itself. What that is saying is that all of the diagonal entries in your table must be ticks. They must be true. So rule number 1 actually has a fancy name. It's called reflexivity. Rule number 2 then also has a fancy name, and it's called anti-symmetry. And it again is very intuitive. So what it says is that if you take any 2 elements in the set, so for all x and y in the set, where x is not equal to y, so we want 2 distinct elements in the set, don't pick the same element twice, then either x must be less than y or y must be less than x. So one of them has to be lower than the other one, but not both. So whichever one is true, the other one then is automatically untrue. What that is saying is that if the table is going to mean something, it has to be the case that it's anti-symmetric, and that's the reason this property has its name. So if you have these ticks on this side of this diagonal down here, then the opposite entries, the symmetric entries, have to be the opposite answer, so it has to be an anti-symmetric table. Now, it's very easy to create a table that obeys those first 2 properties. You could do it in your sleep. However, with just those 2 properties alone, it won't be the case that your table necessarily has a meaning. It won't be the case that you can necessarily use it to create an order on your set of elements, a picture like this. The final property is the one that it's much more difficult to get your table to obey. And indeed, if you were just naively making your table up, it almost certainly is not going to obey this property. But this is the one that is absolutely crucial in order to make it mean something, in order to make it the case that you can go from the table to a picture like this. So this final third property is called transitivity, and it says that if you have three elements within your set, which we'll call x, y, and z, then if it's true that x is less than or equal to y, and it's true that y is in turn less than or equal to z, then it must be true that the relationship between x and z in your table, it must be true that x is less than or equal to z. So this takes 2 points in the table, and then there's a third entry point in the table that has to be related to the answer in these two. So this is much more complicated to make your table obey this property, but this is obviously absolutely crucial. Clearly, if you've got a picture like this, it's going to obey this property. So hopefully it's fairly obvious to you how, if you have a set with a picture like this, i.e. a intuitive order in a picture form like this, hopefully it's obvious that if you turn that into the abstract table like so, then obviously it's going to obey these three properties. We now need to go the other way. I need to convince you that if you have a set with one of these abstract tables that obeys these three properties, that can go the other way, that you can use that to make an intuitive picture of the order like so, because then I've truly shown that they're interchangeable, that they are equivalent. So I'm going to do this now with this picture that I've drawn here. So we're now going to imagine that we've got a much more complicated set, S, so it's going to have more than 3 elements here. So I've drawn the table here, so we've got all the elements of S up here and all the elements of S up here, down here, and then all the entries here are going to be filled in with ticks and crosses, and we're going to say that it obeys these 3 properties, and I want to convince you that from that I can go to having a picture of all of the elements in a great big line. So let me explain how. So if you wanted to put the elements in a line using this information, how would you start? Well, you'd start by just picking one of the elements of the set. So pick a random one that you're going to start with, and then put that on your line. And then you go to element number 2, so you pick another element in the set, and then all you need to know is, does it need to go on the right-hand side of this first element, or does it need to go on the left-hand side of this first element? So you just need to ask which one's less than the other, and the anti-symmetry property ensures that that is well defined. Without this, you're not going to know, because if it were true both ways, then you don't know which way round to put them, but the anti-symmetry means that it's only going to be true one way, so it's obvious whether you need to put it on this side or this side. So if it's bigger than it, you put it on this side, like so, and we're assuming for this picture that it was bigger than it, so we put it on the right-hand side here. If it's less than it, you put it on this side. Then you go to element number 3. And now there are 3 positions that element number 3 could go in. It could go up here, it could go in between the two, or it could go down here. So just compare it to this element, element number 2 here, and ask, is it bigger than element number 2? And if it's bigger than element number 2, you're going to put it here. And the fact that transitivity is true means that then element number 1 is forced to be smaller than element number 3, because element number 3, we've already said, is greater than element number 2, and we knew already that element number 2 was greater than element number 1. So if our table obeyed this property, which we began by saying it's going to, then it's well defined. Element number 3 has to go up here. Then the other option is it could be smaller than element number 2 but bigger than element number 1, in which case it will go in here, or it could be smaller than element number 1, in which case it goes down here. And again, that's well defined because transitivity ensures that if it's smaller than element number 1, then it has to also be smaller than element number 2, because element number 1 was smaller than element number 2. So transitivity ensures that this decision process is well defined, that you're not getting to situations where there could be more than one answer. It forces that there's only one answer for where your next point that you're adding in is going to be. So now if we imagine that we've done this loads of times and we've got now loads of points in a line, if we imagine the nth point, so let's now imagine adding a point on here. So we've only got 6 on our picture. So we're adding in element number 7 from our set S. Where does it go? Again, it's got all these possible positions. It could go here, 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 it could go here. You need to make that decision by comparing it to all of these points. And transitivity ensures that it's well defined, because it ensures that wherever its position is going to be, it forces it to be less than or equal to all of the elements above it. So if its position is going to be here, for instance, that means it's going to be less than or equal to this element here. Because transitivity is true, and this element is smaller than these two elements, that forces that this element is indeed going to be smaller than these two elements because of transitivity. So transitivity ensures it's well defined. Likewise, the other way. It's here, so it's less than or equal to this element. By transitivity, it forces it to also be less than or equal to these elements in the table, which means that this is pictorially well defined. Imagine the situation where if you had a crap table that didn't obey this property, then you could end up with a situation where this element is, you're adding in this 7th element, and in the table it says it's less than or equal to this element, but greater than or equal to this element, so you want to put it there. But what if, when you compare it to this element down here, this element is actually greater than this in the table? That would be a nightmare. It would mean that you don't know what to do. The picture isn't well defined. And the fact that transitivity is true in the table means that this is going to be well defined, and you can therefore create a picture in this way from a table that obeys these 3 properties. And I hope I've convinced you of that there. So a set with an order is called an ordered set. Now on to the main topic of the video. What is meant by an ordered field? Well, the first thing to say, it is not, repeat, it is not just a field with an ordering on it. It is a field with an ordering on it that interacts nicely with the algebraic properties of the field, the addition property and the multiplication property. So an ordered field is a field F such that it obeys these 2 properties. So these are the axioms, the additional axioms, that this structure, which already obeys all of the field axioms, already obeys all of these axioms of the ordering. In addition, it has to obey these if it's going to be called an ordered field. And we're going to spend the rest of the video trying to understand what these mean. So firstly, you will be familiar with these sort of properties because throughout your naive maths life as a child in school, you will have been using these properties when you used either the rational numbers or the real numbers, which are both ordered fields. So property number 1 is, but they are not given, they have to be defined, they have to be added on, you have to insist that they are true. So we have to make sure that this ordering that we're defining on our field is nice in order for these to be true. If you just took a random ordering on your field, it wouldn't obey these. You have to pick a very nice ordering to make it obey these. And of course, you've been using that beautiful ordering on the rational numbers and the real numbers when you've been doing maths in school, which is why it obeyed these 2 properties. So property number 1 is that if you have an element x that is less than or equal to an element y, then if you take some a and you add it onto each of these elements, so you get the new element, which is x plus a within your field, and the new element, which is y plus a in the field, then it remains true that x plus a is less than or equal to y plus a, and that holds true for all x, y, and a's in the field F. The second property is that if you have, again, 2 elements, x and y, and x is less than or equal to y, and then you take another element which we'll call alpha. I don't know why people suddenly switch to using the Greek letter here rather than the Latin symbol, but that is convention. So if we take some alpha, which is greater than 0, which is an element of the field, then if you multiply alpha with x and y, so you get the new element in your field, which is alpha x, and you get the new element in your field, which is alpha y, then it again remains true that alpha x is less than or equal to alpha y. So the rationals with their normal ordering that you've all intuitively known from school, i.e. that normal line that you put them on in school level maths, that ordering that obeys these two properties. However, if you were to mess it up, if you were to put them in some totally random order and accept that as the order that you want to have on the field of rational numbers, then it's still got all of its algebraic properties, but those algebraic properties are not going to interact nicely with the order anymore. They're not going to obey these two properties. And what I'm actually going to now show to you is that there is only one ordering that you can put on the rational numbers such that they will obey these two properties, such that they will be an ordered field. There's no other order that you can put on the rational numbers. It would be cool if there was, but it doesn't exist. And we're going to explore the reasoning for that now. So, let's start really abstract then. So we're not going to talk specifically about the rational numbers, we're just going to deal with an abstract general field f. Now we know that this field f is going to contain the element 0 and it's going to contain the element 1, the additive identity and the multiplicative identity. So the first thing that I want to show you is that if it's going to obey these two properties, then 1 must be greater than 0 in this ordering. So the way we can do that is by proof by contradiction. So assume the opposite is true. Assume that 1 is less than 0, so the multiplicative identity is lower than the additive identity. Then what we can do is, it must be the case, then if this is true, that minus 1 is greater than 0. The reason is that you can add on to both sides of this inequality here minus 1. So we can use this property here. So we're going to take a as minus 1. So if you add on the inverse, the additive inverse of 1 onto both sides, which is called minus 1, then this is going to happen. So 1 plus minus 1, of course, by definition, that's going to equal 0. And then on the other side, we get 0 plus minus 1, which is just going to give us minus 1. So we've then got the statement that minus 1 is greater than 0. So if 1 is less than 0, then instantly, by property 1, you can get to the fact that minus 1 has to be greater than 0. Now, this is a problem. You can't have minus 1 greater than 0 and have property number 2 true, because if minus 1 is now greater than 0, then we can take minus 1 as the alpha here, and we can just multiply both sides of this by minus 1, and the inequality should still hold true. So multiplying 0 by minus 1, of course, you still get 0, but multiplying minus 1 by minus 1, and you get 1. So you'll get then that 0 is less than 1, so 1 is greater than 0, but we started off by saying that 1 was less than 0, so you can't then have that 1 is less than 0. It must be the case that 1 is greater than 0. Just to add a little bit of background, why is minus 1 times minus 1 equal to 1? Well, that comes from field theory. So if you want, when you insist that fields obey distributivity, in fact, it doesn't even need to be a field. A ring, you insist, obeys distributivity. It forces it to be the case that the additive inverse of the multiplicative identity multiplied by itself makes the multiplicative identity. So we can demonstrate that here. So if you imagine 1 plus minus 1, that of course is 0. If you imagine timesing that by minus 1, of course the answer is going to be 0, because 0 times anything in a field is 0. So we know this is 0, but we can now apply the distributive law onto this thing that we've created here. And we can say that this is 1 times minus 1, which is going to be just minus 1, because this is the multiplicative identity and multiplies by anything to give itself, plus minus 1 times minus 1. So whatever the answer to this is, it has to be something that adds to minus 1 to give 0, i.e. it has to be the additive inverse of minus 1, the additive inverse of the additive inverse of 1, but that of course is just 1. So there's your little proof from field theory, from algebra, that minus 1 times minus 1 is equal to 1. So if 1 was to be less than 0, you arrive at a contradiction here, so it can't be less than 0. It must be the case that 1 is above 0 in an ordering that obeys these properties. So let's go further with our derivation of meaning from this. So we now have that 0 is less than 1. We can now apply property number 1 again, and we can say, let's add 1 onto both sides. And this inequality must still hold true. So if you add 1 onto both sides, you get 0 plus 1 must be less than 1 plus 1. So 1 must be less than, and what is the name for 1 plus 1? Well, we call that number 2. The multiplicative identity added to itself in any field, we call that 2. So we now have that 1 must be less than 2, and we can continue this on. So adding 1 onto both sides again, we get that 2 must be less than or equal, must be less than 3. So we're building an order here for the elements in our field F. And in fact, what this shows is that if you have an ordered field, that field must have characteristic 0, i.e. it cannot be one of these finite fields where it loops back on itself. The reason being is, let's say it looped back on itself at the number 4. So if you went on with this and added 1 onto both sides, so you took 2, added 1, you get 3, but then 3 plus 1, that number that is 1 plus 1 plus 1 plus 1 4 times, let's say now that suddenly comes back to the element 0, it's equal to 0, i.e. the field has characteristic 4, that doesn't work with these axioms at all. In fact, it doesn't work even with the order axioms, because suddenly we're going to get then that 3 is less than 0. But that disobeys transitivity, because 3 was less than 2, 2 was less than 1. Sorry, 3 was greater than 2, 2 was greater than 1, and 1 was greater than 0. But suddenly you've got that 3 is less than 0. That disobeys this law here. It breaks transitivity. So you can't have it the case that the field has a non-zero characteristic. All of these numbers, all of these elements of the field that you construct by adding 1 to itself a certain number of times, they all have to equal different elements in the field. You can't loop back round again as you do in the finite fields. It has to have characteristic equal to 0. And we know that any field, or hopefully you know from algebra, that any field with characteristic 0 is always going to contain as a subfield a structure that is isomorphic to the rational numbers, and that's fairly intuitive. If it's the case that it has to contain separate elements for all of these ones added to themselves a certain number of times, then of course it has to contain all of the positive integers. And because it contains all of them, it has to contain all of their additive inverses, so all of the negative integers. So a structure that is isomorphic to the ring of integers has to exist within your field. And because it's a field, it then has to contain all of their multiplicative inverses, which means that then it has to contain the whole of the rational numbers, because after all, the rational numbers is what you get from turning the integral domain of integers into a field by putting on the minimum number of elements you could in order to get an inverse, a multiplicative inverse for every element. So any ordered field, therefore, is going to have a subfield inside of it that is isomorphic, i.e. equal to the rational numbers. And that's certainly true for the real numbers that are going to be an ordered field. They have within them a subfield that is the rational numbers. So now we know that our ordered field has to contain all of the rational numbers. Let's continue working out what order all of those rational numbers have to be in. So at present, what we've got is where all of the non-negative integers are. We've got this line 0, 1, 2, 3, 4, 5, etc. And we could continue going on, and we did that by just using property number 1 and adding 1 onto each side of our inequality. And we know that all of those elements have to be separate elements in the field, because if it ever looped back around, it would suddenly disobey transitivity, so it couldn't possibly be an ordered field. None of the finite fields can have orders put on them such that it obeys these properties and is an ordered field. You can certainly put orders on them. You can take the finite fields and put orders on them, but those orders are not going to obey these two axioms here, so they don't qualify as ordered fields. They would literally just be fields with an order property defined on them. Fields with an order, but not ordered fields. Now, let's carry on. Let's do all of the negative integers now. So we go back to our inequality 0 is less than 1. This time we're just going to add negative 1 onto both sides. So -1 added onto both sides. -1 plus 0 is -1. 1 plus -1 is 0. So then we get that -1 is less than 0. So we now know that -1 needs to go here. And then we can continue on adding -1 onto both sides. So then we get -1 plus -1 is going to equal -2. 0 plus -1 is equal to -1. So we then get -2 must be less than -1. And you go on like this. And of course, the reason we're using these symbols, -1 plus -1, we use this symbol -2 for it because it is going to be the additive inverse of the symbol that we've called 2, which was defined to be 1 plus 1. So of course, -1 is the additive inverse of 1. So if you have -1 plus -1 and you add that to 1 plus 1, associativity and commutativity, in fact not even commutativity, just associativity comes into play there, and of course they cancel out and are going to give you the additive identity. So that's why we use this nice symbol here, because it is truly the additive inverse of -2. So you then end up, of course, with the fact that all of the integers are in this line like so, which of course is the intuitive line that you've used all your life. So now let's try and add the rest of the rationals into our line here. So let's take, for example, a half. So how do we work out where a half is going to be here? Well, just ask some questions. Could we put a half less than 0? Could we have an ordering on the rational numbers where half somehow was ordered below 0 and it still obey the axioms of an ordered field? Well, the answer is no, and the reason is that we can, if this were true, if this inequality were true, and it's true that it also is going to obey the axioms of an ordered field, then we can multiply both sides by 2 because we've already established that 2 is greater than 0. So using axiom number 2 of an ordered field, we can multiply both sides by 2 and the inequality should still hold true. And that, of course, gives a half times 2 is 1 and 0 times 2 is 0. So that would tell us that 1 is less than 0, which is nonsense. We've already established that that's nonsense. 1 is here already in the order. So this is contradiction here. So this cannot be true. So the other thing must be true, that a half is greater than 0. But now that a half is greater than 0, we know that we can multiply both sides of an inequality by a half, and the inequality still has to hold true. So we, in particular, can take the inequality 1 is less than 2, multiply both sides by a half, and we then get a half is less than 1. And we've now got exactly the position where a half should be if we're going to add it in here. It should be between 0 and 1. Now finally, to show you that the position of any rational is instantly fixed in this line as soon as you assume those ordered field properties. So how do we do this? So let's say we have our generic rational a over b, and we want to know where it needs to be in the great line. Well, in order to do that, what you need to do is potentially compare it to absolutely every single element that is already in the line and ask, is this rational that we're trying to position, is it less than or equal to this element, this element, this element? And that's how you'll then find its position in the line. So I therefore need to tell you how you can find out whether it is true that it is less than or equal to any other element that is potentially in this line. Or any other element that's potentially in this line will be another rational. It will be something of the form c over d. Now, of course, if it is one of these integers, then d will just equal 1. But more generally, we might have put loads of rationals already in this line that you're also going to have to compare this element to. So more generally, it will be something of the form c over d. And the way that you can find out whether this inequality is true, so there's a question mark here, you're asking this question, is it true that this is equal to this? Well, what you can do is assume that these denominators are both positive integers. And the reason you can do that is even if the rationals themselves are negative, you can always make sure that the negative is absorbed up here at the top. So the integer in the top here is going to be negative. Oh, and by the way, I should have specified that when we write rationals like this, we're meaning one of them, the numerator is an integer and the denominator is a non-zero integer. So you can always make it so that if the rational is negative, that the negative is in the numerator rather than the denominator. If we're talking, going back to the actual construction of the rationals, you can pick an element within the equivalence class of fractions that are all the same when you cancel them down. You can pick an element such that the denominator is a positive integer rather than a negative integer. So do that in both of these cases. Make sure that your denominator is not negative. Then if this inequality were true, we can multiply both sides through by b and through by d. So multiplying both sides through by b, it cancels here, and then you get b times c over d. Multiplying both sides through by d, you then get AD, and it cancels here. So it should be the case that this is true. AD is less than or equal to BC. Now all of these are integers, so when you multiply the two of them together, you're going to get an integer answer. So now this is simpler because you're just asking, is this integer less than or equal to this integer? And we've already positioned all of the integers. So if this were true, this would have to be true. So all you need to do is ask, is this true? And if it's the case that it is true, then yes, this is true. If it's not true, then this is not true, and it's the other way round. So that's the way that you can, when you're trying to position this new rational in your line, you can actually go through every single element that's already in the line and ask, is it less than or equal to each of those elements? And that's how you can get the answer of where it has to be. So what have we learned here? We actually have learned something quite incredible. So if you set your field equal to the rational numbers and you want to put an ordering on that rational numbers such that it's going to obey the axioms of an ordered field, there is only one way you can do that. Everything is set in stone the moment you want it to obey the axioms of an ordered field. Instantly, the positions of all of the integers within this field are set in stone, and then moreover, all of the other rationals, all of the things of the form a over b, their position is also determined because I've shown you, you can work out its position. If you're assuming this axiom of an ordered field, which says that the inequality must hold true if you multiply through by a positive element, then that instantly fixes where every single rational must go from the fact that we've already know that where all the integers go is fixed because of what I've just shown you. If this is true, this has to be true. So the positioning of the integers fixes the positioning of all the rationals if you're requiring it to obey the axioms of an ordered field. So there is only one ordering that you can put on the rationals that is going to obey these axioms, and that's the ordering that you've been using for years, the intuitive ordering. And hopefully it's obvious to you that that intuitive ordering does indeed obey these properties. Indeed, you've been using them for years. You've been picturing them in your head. You have a pictorial understanding of what these mean in your head. We've also discussed that any larger ordered field must contain as a subfield the rational numbers. So the rational numbers is the smallest of all of the ordered fields that potentially exist. So the real numbers, which we will move on to in the next video, which was concocted to be a mathematical model of one-dimensional reality, it is going to be an ordered field, and we'll see why. But what that instantly means is that inside of it, as a subfield, is going to be the rational numbers with the ordering that we all know and love from years of school level maths. We'll end there. Thank you for watching this video. I hope you haven't found it too boring, and I hope you've learned something.